All right, now we want to look at an important theorem called intermediate value theorem. Intermediate value theorem, or IVT. Abbreviation is IVT. So this theorem says let f of x be a continuous function on the interval a to b then for every m, for every value m between f of a and f of b, there exists c between a to b such that f of c is equal to m. In other words, if f is a continuous function, then every intermediate value will be taken by the function. So let me sketch a graph and explain about this theorem. So you have a continuous function. Continuous function, we know that, intuitively it means that there is no hole or break on the graph of the function. So we have, let's say, some point A here and some point B here. And this is f of A and this is f of B. And then, so see, you have two endpoints, A and B, and the function is defined between A to B. You have f of A, the output for A, f of B, the output for B. And then there is some m value. M value is supposed to be a number between f of A and f of B. So in this case, could be something like this, let's say. Now, this intermediate value theorem says that this intermediate value will be taken by the function, meaning that there is some c value between a to b that f of c is m. So see, m here, which is a number between f of a and f of b, will occur as an output of f for at least one input c, which is between a to b. So let's say this c here in this example, c would be here, and this value will be f of c. So basically, of course, this theorem needs a proof, right? But if I want to explain the idea for you, is that, because you have a function which is continuous, therefore there is no hole or break. So when you want to move from f of a to f of b, you will pass through every intermediate value at some point. You are not allowed to jump and bypass any intermediate value. You have to pass through every intermediate value. So when you start from f of a, you go to f of b. Every intermediate value will be taken by the function. Right? So, but if the function is not continuous, then you can have a jump and some intermediate value may not be taken by the function. All right, so first let me give you a remark. A condition of continuity, or the assumption of continuity, is required in intermediate value theorem. For example, see the graph below. Let's say, for example, this graph. So let's say this is A and this is B, right? And let's say if you have some intermediate value here, for example, let's say this is, for example, 2, and let's say this is 4. And let's say this is m equals 3. See, this red line does not pass through the graph, which means m equals 3 will not be taken by the graph by the function itself. So there is no c value such that f of c is equal to 3. Right? Because see, the graph has two pieces. One piece is this and one piece is this, and none of these two pieces have any intersection with this horizontal line, which means that m equals 3 is not taken by the graph, which means it's not an output for any of the inputs between A to B. Okay, so that's one remark. Now let's look at an example. Let's say, for example, consider f of x equals x squared on the interval, let's say 1 to 4. Find all values of C in the statement of IVT corresponding to m equals, let's say, 5. So here, what are the values of A and B and f of A and f of B? So here, A is equal to 1, B is equal to 4, and then f of A is equal to 1, f of B is equal to 16, right? And here we have m is equal to 5, which is between f of A and f of B. And f of x equals x squared is continuous everywhere. So by IVT, there must exist a value C between 1 to 4 such that m is equal to f of C, right? So see, IVT says any intermediate value m will occur as an output, as a f of C value for some input C between A to B. So here, what is the C value? Now m is equal to 5, which is equal to x squared. So that means x is equal to plus minus root 5. But our C value must be between 1 to 4, as we said here. So minus root 5 is not between 1 to 4, of course. So we reject minus root 5 as it is not between 1 to 4. That means c is equal to root 5, which is between 1 to 4. Okay, another example, let f of x equals sine 2x. Let's say on the interval 0 to let's say 3 pi over 4. And let m equals minus 1/2. Find the values, values of c as stated in the statement of, given in the statement of IVT. Okay, so again, here we have a function defined as some interval a to b. So what is f of a and what is f of b? So a is 0, b is 3 pi over 4. Then f of a will be sine 0, which is 0. F of b is sine 3 pi over 2, which is minus 1, right? Sine 2x, if x is 3 pi over 4, sine 2x will be sine 3 pi over 2, which is minus 1. And m is minus 1/2, which is between f of a and f of b. Now m equals minus 1/2, bigger than f of b, less than f of a. See, that's why I said in the statement of the theorem, I said m is between f of a and f of b. I did not say bigger than f of a, less than f of b. Because in some exam, that depends on whether f of a is less than f of b or f of b is less than f of a. In this case, f of b is less than f of a and m is bigger than f of b, less than f of a. But in this case, for example, previous example, m was bigger than f of a, less than f of b. So in any case, I can say m is between f of a and f of b, right? So that's why I use this sentence rather than saying that m is bigger than f of a, less than f of b, because it's possible that f of b is the smaller value and therefore m will be bigger than f of b, less than f of a. So m is between f of a and f of b. So let's look at the unit circle. So this is 0, and then we have sine 0, 0, and then this is 3 pi over 2, and sine, the point is 0 and minus 1, therefore sine is minus 1. And then we have m equals minus 1/2, which will be taken by the sine function at this angle. So what is the angle with sine of minus 1/2? Pi plus pi over 6, because sine pi plus pi over 6 is minus sine pi over 6, which is minus 1/2. So what f of x here is sine 2x. Now the angle must be pi plus pi over 6, which means 2x must be pi plus pi over 6 in order for sine to become minus 1/2. Right? Now, then let me say if we set sine 2x equals minus 1/2, So the solution on 0 to 3 pi over 4 will be, because our interval is 0 to 3 pi over 4, so 2x equals this angle pi plus pi over 6, which is 7 pi over 6, and therefore x will be 7 pi over 12. 7 pi over 12 let's see if the screen is freezed or you have to stop share. Okay, now it's good. Yeah, 7 pi over 12. 7 pi over 12 is of course between 0 and 3 pi over 4. You know, you can easily check this because forget about pi. 0 to 3 over 4, 3 over 4 means 0.75. And 7 over 12, of course, is less than 0.75. But do we have any other solution, do you think? Between 0 and 3 pi over 4. So let's look at the next solution of this equation. So it's like, let's say first solution. Now let's see whether there is another solution as well. See if 2x, what is the other solution here? Because the other solution will be, if you want sine to be minus 1/2, you could be here as well, which is 2 pi minus pi over 6. So if 2x equals this angle here is 2 pi minus pi over 6. So if 2x is equal to 2 pi minus pi over 6, that means 11 pi over 6, and then x will be 11 pi over 12, which is not between 0 and 3 pi over 4. So this one we reject. So that means c equals 7 pi over 12. This is the only value of c. C between 0 to 3 pi over 4, such that f of c is equal to m as predicted by IVT. So in this example, we also found one value for c, that f of c equals m. Previous example, we also found only one value. But you know, the value of c does not have to be unique. There could be more than one c value. So let me give as a remark here. Remark, the value of c c as stated in intermediate value theorem does not have to be unique. In other words, we may have more than one c value such that f of c equals m. You can have more than one c value with f of c equals m. Okay, now here's the example that shows we can have more than one c value on an interval. Let's say consider y equals sine x on the interval that says 0 to 5 pi over 2. So this is how the graph looks like. 0 sine x. This is 0. This is 5 pi over 2. And this is 2 pi. And now, let's say with m value, with m equals 1/2. So this is m value of 1/2. So now m equals 1/2. That's between f of a, f of 0, which is 0, and f of 5 pi over 2, which is 1. Right? So m is between f of a and f of b. And the solutions of f of c equals m equals 1/2 equals sine c are which solutions? So as you can see in the picture, this intermediate value crosses the graph at more than 1 point. So we have more than one c value. So I could call this one, for example, c1, c2, and c3. So the picture suggests that we will have 3 c values with this property, and the calculation confirms this, because if you want 1/2 to be sine c, then c could be pi over 6, or c equals pi minus pi over 6, right? Sine pi minus theta is same as sine theta. And of course, c equals 2 pi plus pi over 6, right? Of course, sine 2 pi plus theta is same as sine theta. And 2 pi plus pi over 6, sine 2 pi plus pi over 6 will be also 1/2. And this could be also, of course, simplified as 13 pi over 6. So 3 c values as expected. And that's it. So we have a continuous function and a closed interval, and one intermediate value, which is taken by the function 3 times on this interval. Okay, so now let's look at an application of IVT. IVT existence and estimating roots of a function. Okay, so suppose that f of x is a continuous function on the interval a to b with f of a times f of b less than 0, then f of x has a root on this interval, meaning that there exists a c value between a to b such that f of c is equal to 0. If f of a times f of b is less than 0, then f of x has a root, meaning that f of c equals 0 for some c between a to b. So how can we prove this? The proof of this is very simple. So let me call this one a proposition. Proposition, in mathematics, propositions are like theorems. There are some statements which have some assumptions and some conclusions, but theorems are more, major ones, and propositions more minor. Usually propositions can be proved using theorems. So how can we prove this? We can easily prove this using IVT. So proof f is continuous. So since let's start with this assumption that says f of a times f of b less than 0. If product of two numbers is less than 0, then what can we say about those two numbers? So this is something from elementary school. If multiplication of two numbers is negative, then one of them should be positive and one of them should be negative, because if both are positive, the product will be positive. If both are negative, the product will be negative. And if one of them is 0, still product will be 0, not negative. So the only possibility in which case you can have a negative number is that if one number is positive and one number is negative, then you can have product of those two numbers become negative. So I can say since f of a times f of b less than 0, we can conclude that either case 1, f of a is positive and f of b is negative. In this case, m equals 0 will be an intermediate value, because m equals 0 will be bigger than f of b and less than f of a. So m is an intermediate value. Intermediate value, and y equals f of x is a continuous function. Continuous function on the interval a to b by assumption, right? Remember, our assumption was that f is continuous on a to b and f of a times f of b negative. So m is intermediate value and this is a continuous function. So by IVT, there exists C between A to B such that f of C is equal to m and m was 0. So if f of C equals 0, that means C is a root for f of x, i.e. C x equals C is a root for y equals f of x. Similar reasoning can be done for case 2. Case 2, if f of, so either case 1 or case 2, f of a negative and f of b positive, then again we can say that m equals 0 again is an intermediate value, so bigger than f of a, less than f of b. So m is an intermediate value and f of c, m is an intermediate value, and by IVT, m equals 0 equals f of c for some c between a to b, i.e. again x equals c is a root for y equals f of x. It seems the screen is freezed. Okay. So this was case one where we concluded that, I think it was freezed here. So here, if f of c equals 0, we said that, well, if f of some number equals 0 means that number is a root for your function. And or case two, if f of a negative, f of b positive, then 0 will be between f of a and f of b again. So in any case, either case one or a case two, m equals 0 is an intermediate value. In one case, 0 was bigger than f of b less than f of a. In the other case, 0 is bigger than f of a less than f of b. So again, m is an intermediate value here. And again, by IVT, we can say that m equals 0 will be f of c for some c. And again, that means c is a root for y cos f of x. So in either case, we are done. We showed that if f is continuous function and if f of a times f of b is negative, then f of x must have a root between a and b. So let's look at an example. Show that y cos x cubed plus x has a root between so let's say x cubed plus x plus 1, x cubed plus x plus 1 has a root between minus 1 and 0. X cubed plus x plus 1 has a root between minus 1 and 0. So what is our function here? So here, f of x is equal to x cubed plus x plus 1, which is continuous on minus 1 to 0, right? Now, how much is f of minus 1? We have f of minus 1 equals minus 1 cubed plus minus 1 plus 1, which is minus 1, and this is negative. What about f of 0? F of 0 is 1, which is positive. So we can conclude that f of minus 1 times f of 0 is negative, right? So I have a continuous function, f of minus 1 times f of 0 is negative. So what can we conclude? So by proposition above, y cos f of x has a root between minus 1 and 0. F of minus 1 times f of 0 is negative, so it must have a root between minus 1 and 0. Okay. So now this is about existence of roots. We can also estimate the roots. So estimating the roots. Estimating the roots of a continuous function. So again, suppose that y cos f of x is continuous on a to b, and suppose that f of a times f of b is less than 0, then by proposition above, above, we know that f of x, y equals f of x, must have a root between a and b, right? Now, see here we have a and we have b here, and f of x must have a root between f of a between a and b. Now, if you want to, well, that's some estimation for the root, because once we know that root is between a and b, that means we have some idea about the root, right? So, for example, we saw that in the previous example, we concluded that this function has a root between -1 and 0. So that means we have some estimation or some idea about the location of this root. But what about if we want to have a better estimation or more exact idea about the location of the root? For example, previous example, yes, then we know that the root between -1 and 0, but their main numbers is -1 and 0. Is it going to be -0.9 or maybe -0.91, -0.1? What is it? Now, if you want to have better estimation, so the next step is that we are going to consider the average of a and b. So must have root between a and b. The next step, consider, let's say, I can call it alpha 1 equals a plus b over 2. See, alpha 1, the average, see the root, we know that it's between a to b. It's possible that the root is the average of a and b. That's one possibility. So then we can have 3 possibilities. So one possibility is that f of alpha 1 equals 0. So then that means alpha 1 is a root. Remember, our goal was to estimate the root. Well, if f of alpha 1 is 0, that means alpha 1 is our root. Of course, it's possible that we have more than one root, but our goal right now is to estimate at least one of the roots between a to b. So if f of alpha 1 is 0, that means, well, we found our root, and at least one root between a to b. Second possibility is that if f of a times f of alpha 1 is negative, then f of x has a root between a and alpha 1. In this case, consider alpha 2 to be a plus alpha 1 over 2. And then look at f of a times f of alpha 2 and f of alpha 2 times f of a. And to improve our estimation. See, this is a, this is b, and this is alpha 1, which is the average. Now, let's say if f of a times f of alpha 1 is negative, that means our root, remember, we are locating the root. We know that it's between a to b. Now, if f of a times f of alpha 1 is negative, that means the location that we are looking for is between a and alpha 1. So then we can look at, so this will be the interval that we are looking for. Then we can look at alpha 2, which is the average between A and alpha 1, right? Because so far I know that there is, first I knew that there is a root between A to B. Then I located it to a root between A to alpha 1. Then I basically traced it to a root between A and alpha 1. Then look at alpha 2. Then you can either have a root between A to alpha 2, or you could have a root between A to alpha 2 to alpha 1. So f of A times f of alpha 2 and f of alpha 2 times f of alpha 1 to improve the estimation. So once, first we knew between A to B, then we trace it to A to alpha 1. Then if we know it's between A to alpha 1, either it's between A to alpha 2 or alpha 2 to alpha 1. So that means we have to look at f of A times f of alpha 2. If it's negative, that means there is a root between A to alpha 2, which means we have improved our estimation. Or if f of alpha 2 times f of alpha 1 is negative, that means there is a root between alpha 2 to alpha 1. Again, that means we have narrowed down our estimation, so we have improved our estimation again. Okay, so similar thing happens if this is the case if we know that the root is between A to alpha 1. If the root is between alpha 1 to B, then you can do the similar reasoning. So for case 3, if f of alpha 1 times f of B is negative, then we can say that there is a root between alpha 1 and B. In this case, consider, again, let's say beta 2 alpha 1 plus B over 2. Then consider f of alpha 1 times f of beta 2 and f of beta 2 times f of B to improve the estimation. Right, so if the root is between alpha 1 to B, then once I consider beta 1 here, again, we can have two possibilities. Either the root which is between alpha 1 to B, we narrowed it down between alpha 1 to B, could be between alpha 1 to beta 1. And in that case, f of alpha 1 times alpha 1 to, I called it beta 2, sorry. In that case, f of alpha 1 times f of beta 2, this number here, will be negative. This number will be negative if the root is here. And if the root is here between beta 2 to B, then this number will be negative. So in any case, we can consider whether this number, calculate this number and this number, find out which one is negative to narrow down the root more than before. So let me show all these in an example to you. So example, estimate the root of f of x equals x cubed plus x plus 1 up to 1 decimal. Root of this up to 1 decimal. So we saw before, we saw in previous example that f of minus 1 times f of 0 is negative. And because f is continuous function, continuous on minus 1 to 0, And so by IVT, we concluded that there exists C between -1 to 0, such that f of C is 0. Now to improve the estimation, what should we do? We have to consider the average of -1 and 0. We should call it alpha 1. Alpha 1 equals -1 plus 0 over 2 equals -1/2. So see, this is 0, this is -1. And this is 0. We already know that the root is between -1 to 0. Now to narrow it down, we are going to consider the half point between -1 to 0, which is -1/2. And then we have to either narrow it down between -1 to -1/2 or -1/2 to 0. Now, how can we do that? We can consider f of, so consider f of -1 times f of -1/2, right? So the root is either from here to here or from here to here. I have to consider f of -1 to f of -1/2. If it's negative, it means it will be here. If my f of -1/2 times f of 0 is negative, it means it will be here. How much is this? F of -1 was -1, and f of -1/2 is 0.375. You remember f of x is x cubed plus x plus 1. So f of -1/2, you can compute it will be 0.375, and therefore the product will be negative. And this is exactly what we are looking for. If the product of f of a and f of b for two values a and b are negative, then we can say that there is a root between those two numbers. So there is a root between -1 and -1/2. So we narrowed down the root to be between -1 and -1/2. In the next step, we consider the average of, see, once you narrow down the root between two numbers, then you can consider an average of those two numbers to narrow it down further. So the average of -1 and -1/2 is -3/4. So -3/4 is here. Then we consider f of -1 times f of -3/4, because we already narrowed down from here to here. So then we can, so the root will be either from here to here. So we have to consider f of -1 times f of -3/4, or it will be between f of -3/4 to f of, it will be between -3/4 to -1/2. So we have to consider f of -3/4 times f of -1/2 in that case. So f of -1 times f of -3/4, this times this is positive, and this times this, f of this times this, f of this will be negative. So well, positive is not what we are looking for, but negative, product of two outputs negative. That means we have a root between these two numbers, -3/4 and -1/2. So there is a root between -3/4 and -1/2. So we narrow it down to be between here to here. Then we have to, if you want to narrow down further, we have to consider half of the average of these two numbers. Average of these two numbers are computed here. It's -5/8. -5/8 is the average of these two numbers. So let me show you here, -5/8. So again, the root could be from here to here or from here to here. So we have to consider f of -3/4 times f of -5/8. And f of -5/8 times f of -1/2. This time, this product will be negative. And that means there is a root between this number minus 5/8, which in decimals is minus 0.625, and this number minus 3/4, which in decimal is minus 0.75. So we narrowed down the root to be between minus 0.625 and minus 0.75. So are we done? How can we know that we have to stop? When should we stop? Remember, this question is asking us to estimate the root up to 1 decimal. Up to 1 decimal means, up to the 1 decimal is the root, for example, minus 0.1, is it minus 0.2? What is it up to 1 decimal? So far, we concluded that the root must be between minus 0.625 and minus 0.75. So imagine the numbers within minus 0.625 and minus 0.75. There are, of course, infinitely many numbers in this range. Could we think about some examples of such numbers? For example, let's say minus 0.63, right? Or minus 0.64. Minus 0.63 up to 1 decimal is minus 0.6. Minus 0.64, again, up to 1 decimal is minus 0.6. So if we continue, let's say, but for example, minus 0.71 is also in this range. Minus 0.71, however, up to 1 decimal is minus 0.7, right? So some of the numbers in this range between these two numbers up to 1 decimal are minus 0.6. Some of them are minus 0.7. So we really narrowed it down. We are sure that the root up to 1 decimal is up either minus 0.6 or minus 0.7, but we are not done yet because we really need to know for sure whether it is minus 0.6 up to 1 decimal or minus 0.7 up to 1 decimal. So let's continue this improvement. One more step. If I continue one more step, what should I do? Again, I have to consider the average of these two numbers, which means the middle number between these two numbers. The result is minus 11/16. So minus 11/16, let me show you in the picture. Minus 11 here. Over 60. So we consider this number. And then we have to, okay, so see again, let's look at the picture. So we know that the root is between this purple one and this green one. So either it will be between this purple one and this blue one, or between blue one and green one. So we have to consider f of minus 3/4 times f of minus 11/16, and also f of minus 11/16 times f of minus 5/8. We did that. The first number turns out to be negative. Second number turns out to be positive. Again, remember, we are looking for the case where the product of output is negative, which happens in the first case. So that means there is a root between this number and this number. This number up in decimals is minus 0.6875. And this number in decimals is minus 0.625. So see, now if you imagine any number between this number and this number, for example, minus 0.67 or minus 0.66 and so on. So all the numbers between this number and this number up to 1 decimal are minus 0.6. Both of these numbers up to 1 decimal are minus 0.6. So any number between them also up to 1 decimal are minus 0.6. So here I can say that since any number between minus 11/16 and minus 5/8 is minus 0.6 up to 1 decimal, we can conclude that the root up to 1 decimal is minus 0.6. This can be verified using a root calculator. And it can be seen that the root up to 1 decimal, that the root of f of x equals x cubed plus x plus 1 is, so if you can just Google a root calculator and just enter your function. It says that the root is minus 0.68232, which is minus 0.6 up to 1 decimal. Okay. Yeah, so this is the way we can estimate the roots up to however decimals we want. So with the estimate up to 1 decimal, if you want, you can estimate up to 2 decimals. But then of course you need much more steps and it will be very long, because you need many steps. But if you do it with a computer, the computer can do the calculation very fast and get the result quickly. And this is the way, the root calculator, when you say search for root calculator. So each of these softwares, they use some algorithms, right, to compute something. So one algorithm to estimate the roots is this method here that we explained, which was a conclusion of IVT, or intermediate value theorem. And one more example we want to do here for IVT. Remember, I promised you earlier that I'm going to prove for you that the range of x cubed plus x is the set of all real numbers. So show that the range of f of x equals x cubed plus x is the set of all real numbers. All real numbers, i.e., it's the set of R. Remember, we were doing this, looking at this example, x cubed plus x. We saw that this is like a one-to-one function, and therefore invertible, and the inverse is continuous on the domain of f inverse, which is range of f. And I promised you that I'm going to show you that range of f is a set of all real numbers. So how can we show that? So let m belongs to R be an arbitrary real number. So how can we show that the range is all real numbers? That means we have to show that any real number m can occur as an output of this function, because range means the set of all outputs, right? So if I show that every real number can happen and will happen as an output for f, that means the range, or the set of all outputs, is the set of all real numbers. So let m belongs to R be an arbitrary real number. Then, so we want to show m is equal to f of c for some c in R. So note, so first let's look at the limit f of x as x approaches to infinity. So this means limit x cubed plus x as x approaches to infinity, which is limit x cubed I can take out, 1 plus 1 over x squared, x goes to infinity. So this will be infinity cubed times 1 plus 1 over infinity. So this is infinity times 1 plus 0, and the answer is infinity. And limit, what about the limit f of x as x approaches to minus infinity? So this is limit x cubed times 1 plus 1 over, again, x squared, x approaches to minus infinity. So then this is minus infinity cubed times, again, 1 plus 0. Again, the answer is minus infinity. Thus, so what can we conclude? So limit x approaches to infinity, limit f of x approaches to infinity is infinity. So that means as x gets larger and larger, f of x, the output of f of x can get bigger than any given number. So they will become bigger than m ultimately, because m is a fixed real number, but outputs get bigger and bigger than any given number, including m. So that means there is some x value for which f of x is bigger than m, right? So there exists, let's say, some a in R such that f of a is bigger than m. So this is because, limit f of x is infinity as x approaches to infinity. So some big numbers, big input for which the output is bigger than any given number. So the output could become bigger than m ultimately. Let's call that number, that the input for which the output becomes bigger than m, let's call the input a. Similarly, there exists, let me call this one b, maybe, it doesn't matter. And similarly, there exists a in R such that f of a is less than m. Again, this is because limit f of x as x approaches to minus infinity is minus infinity. So limit f of x equals minus infinity means the outputs will get, ultimately, they'll get smaller than any given number, any given m value. So ultimately, the output will become less than m for some, at least for one input a. So I'm calling that input a, and for input a, f of a will be less than m. And thus, so if there exists a in R, and of course I can assume that this a is less than b, right? Because this a could become x approaches to minus infinity, limit f of x is minus infinity. So this a could be towards minus infinity. So this is, let's say, this could be a towards minus infinity, and this could be b towards positive infinity, right? And f of a could become less than any given number, such as m. F of b could become bigger than a number, such as m. So let's see, the graph of function looks like this. Let me draw the graph, maybe it helps you. See, this is how the graph looks like. See, so let's say b could be here as x approaches, m could be somewhere here. Maybe I can draw the picture here. Limit f of x as x approaches to infinity is infinity. Limit f of x as x approaches to minus infinity is minus infinity. And m could be somewhere here. So of course there exists some m, some b value here, where with f of b bigger than m, bigger than m. And of course, there is some a value here. With f of a less than m. So towards minus infinity side of x-axis, there is some a value that f of a could become less than any given number, such as m. Towards infinity side of x-axis, there must exist some b value that f of b is bigger than any given number, such as m. All right, so what can we conclude? Thus, f of x equals x cubed plus x is a continuous function. Is a continuous function on the interval a to b. F of x is a polynomial. And m is between f of a to f of b. So by IVT, we can say that there exists some c between a to b, such that f of c equals m. Hence, we conclude that a range of f is equal to a set of all real numbers. Because this m was an arbitrary real number, right? Remember, this m was an arbitrary real number. And we showed that it must be in the range. So every real number must be in the range of f, which means range of f must be the set of all real numbers, right? And this picture also shows that any number m that you consider, we can find some a with f of a less than this, some b with f of b bigger than that. And by IVT, because the function is a continuous function, the function must cross the graph at some point c. So m must be equal to f of c for some c, which means m must be in the range. Every real number must be in the range. So range of this function must be the set of all real numbers. Okay, guys, so this is end of chapter 1, and we'll have test 1 from chapter 1 up to end of lecture 6. End of today lecture, which is lecture 6 of today lecture. Okay, so yeah, I'll also upload the assignments, and yeah, please let me know if you have any questions. You can feel free to send an email to me or attend the office hours. Okay, so thank you guys, and see you next time.